This presentation is a part of a lecture series on the C++ programming language by Michael Adams at the University of Victoria in Victoria, Canada. For those of you who might be interested, a copy of the slides for this lecture series can be downloaded from the website whose URL is given at the bottom of this slide. In this section, I'm going to be talking about function templates, where a function template provides a mechanism in C++ for specifying a family of functions that can be used, for example, to facilitate a style of programming known as generic programming. Before I start talking about function templates, I first want to introduce the motivation for function templates. So, for example, suppose that we have the need to compute the maximum of two values in our code. So we have two int values, x and y, and we want to compute the maximum of the two values. So we have this function here, it checks to see is x greater than y, and if it is, it returns x, otherwise it returns y. And the return type you can see is int from this code. But then we might also want to take the maximum of two doubles, for example. Then we need a function which looks something like this. It takes two double parameters and it returns a double, and basically the body of the function looks very similar to what we had above here. Well, actually, it's identical. And then this sort of code can repeat. This code pattern can repeat over and over again because maybe you want to take the maximum of two longs or two long longs or an unsigned long or a long double, etc., or other types for which the greater than operation is defined. Well, we really don't want to have to keep writing these functions over and over again because they all basically look the same. And in particular, all of these functions here have the same general form to them. For some type capital T, the code looks like this. We have a function which takes two parameters of type T. So the first parameter has type T, the second parameter has type T. The code body looks like this, and the return type is type T. It would be nice if we could somehow in C++ just write this function once in a generic kind of way, kind of like what I've shown here. And this has the advantage that we don't have to repeatedly type the function over and over again. We don't have to keep debugging multiple versions of a function, testing multiple versions of a function, and then when we're looking at code, our eyes do not have to parse many copies of an almost identical function where just a few type names are changed. And in effect, what we'd like to do is we'd like to have a function where we can parameterize the function on some type T. And in fact, we can do this in C++, and this can be accomplished by using function templates, which I'll be discussing next. One type of template in the C++ programming language is what's known as a function template. So a function template is simply a family of functions that are parameterized by one or more parameters. And these parameters to the template can be either a non-type, for example, an integral constant like int or unsigned int, or a type, which can be a built-in type or a class type, or a template, or a parameter pack in the case of variadic templates, which we'll talk about much later. The basic syntax for a template function looks as follows. We start out with a keyword template, which is introducing something that's a template which comes after it. This is followed in angle brackets. We have an opening angle bracket here and a closing angle bracket here. The thing between the angle brackets is a list of parameters for the template. And then this is followed in the case of a function template by the function declaration, which is either a declaration or a definition of a function. And in the parameter list here, we distinguish between these different kinds of parameters, non-type versus type versus template versus parameter pack. There's different ways to designate in the parameter list what kinds of parameters they are. In the case of a parameter which is a type, we introduce it by either the class or type name keywords, so that would appear in the parameter list here. In the case that the parameter is a template, we use the template keyword, and a template parameter is identified by the class keyword. And then in the case of a non-template parameter, we just use the type name, so bool or int or whatever the type name is of the non-type parameter. So for example, if the parameter is an integer value, we would use int. And then at the bottom of the slide, I have a very simple example of the declaration and definition of a function template. So you have a function max, which takes two parameters and returns the maximum of those two values. So this is a declaration of this template function. So again, it starts out with a template keyword, which is basically saying the thing that follows it is a template. This is immediately followed by the parameter list for the template. In this case, you can see that the parameter list has a single parameter, which is called T. And T is specifically the name of a type, because this class keyword here says that the parameter is a type. You could also put type name here. It makes no difference. Class and type name mean exactly the same thing in this context. Some people prefer the use of type name because in some sense it's a more accurate description of what it is that you're doing because you're introducing a type here. It doesn't necessarily have to be a class. It could also be a built-in type. On a lot of the slides, I tend to use class just because it's a little bit less typing than type name. But it really doesn't matter. Both of them mean the same thing. Then we go on to the actual function declaration here. So we have a function. The return type is t. The function's called max. It takes 2 parameters of type capital T. And we have a function declaration. We can also have a definition of the function, in which case we have to provide the body of the function. So again, we start out with a template keyword, followed by the parameter list for the template in angle brackets, followed by the actual definition of the function. So the function returns type T, takes 2 parameters called x and y, which are of type T, and then we have the body of the function here, which just checks to see is x bigger than y, and if it is, it returns x, otherwise it returns y. In other words, it's returning the maximum of these 2 values, and this is our template code. So now we could compute the maximum of any 2 elements of type T, where T could be anything, and we don't have to keep rewriting this function over and over again. The only requirement is that the type T must implement the greater than operator so that we can actually successfully do this comparison. Because a function template is essentially a whole family of functions, the question might arise as to how do you specifically identify one member of this family of functions if you need to do so. And in a language, there's a syntax that allows you to do this, where you can write the name of the function followed by, in angle brackets, the template parameters. And this is the way that you can identify a specific member of a family of functions that's represented by a function template. So to put this in more concrete terms, suppose that we have this function template max here. So there's a single template parameter, which is a type called T. It's a type because of the class keyword here. So the function has a return type of T, and it takes 2 parameters of type T. If we wanted to refer to the particular version of this function in the family of functions represented by this template that corresponds to T being chosen as int, we can identify this by writing max and then in angle brackets int. So this refers to, of all of the different functions that are associated with this family of functions, in other words, associated with this template here, the particular one where T is chosen as int is the one called max int. And similarly, if we wanted to refer to the particular version of this template where double is plugged in for capital T, in other words, the function double max double double, we can refer to this using the syntax like this. Max and then in angle brackets double. A few other comments I need to make about function templates. One is that the code for a function template is only generated by the compiler at the point where you instantiate the template. So instantiate is just a fancy way of saying use. So in other words, the compiler only generates the code for a function template at the place where you actually try to use that template. In other words, at the place where you actually try to plug in template parameters for that template and try to use it. And if you stop and think about it, this would be the way that the compiler would have to work, because the alternative would be in advance of the point where you actually try to use the template, the compiler automatically pre-generates every possible template parameter that you could plug into the template. And you could see that this would pose some problems, right? Because for example, for this max template here, there's an infinite number of choices for T that we could plug in here. Basically any type for which we can compute a maximum value, which is basically anything that's sort of numeric in its nature, we could plug in here, and there's infinitely many types we could choose. So if the compiler generated the code for a function template before we use it, it would have to generate infinite numbers of versions of the function to cover all the possible template parameters we might plug in. So the only practical solution is that at the point where you use the template, and then the compiler knows what particular template parameters you want to plug in, at that point it actually generates the code for the template. Now the reason why it's important to understand when the compiler is generating the code for the template is this has implications in terms of where you place definitions for function templates. And in particular, the definition of a function template has to be visible at the place where you actually instantiate the template. In other words, at the place where I actually try to use this max function, for example, in my code, it's not good enough just for the compiler to have this declaration here. It also needs to see the definition. In other words, there needs to be the part of that actually shows the body of the function for max appearing here as well, which would turn this into a definition. And the reason why you need a definition is because, again, the compiler only generates the code for the template function when you try to use it. So when you try to use it, it has to know what the definition of the function is so that it knows what the body of the function is so it can actually generate the code for that particular template. And for this reason, often function template definitions appear in header files. This is not always the case, but most typically they tend to appear in header files. But the most important thing is they absolutely have to appear or be visible at the place where you're actually trying to use or instantiate a template. And then lastly, I just want to point out that template code only needs to pass basic syntax checks at the point where you're just, when the compiler is first looking at the template declaration or definition. It's only when you instantiate the template that a more rigorous kind of checking takes place. This is important to understand because if you have some template code in your program and you never instantiate the template, it's possible that you could have dormant bugs that you're not aware of, that as soon as you actually instantiate the template, the code will fail to compile, simply because the basic checking that's done before you instantiate the template doesn't cover all the possible types of errors that you could have in your code. So it's always a good idea when you're testing your code, make sure that if you have templates that you always actually instantiate them. On this slide I have a few examples of function templates. So the first one is a function template called min. It has a single template parameter called t, which is a type because we have the class keyword here. We could also say type name, it makes no difference. The function takes two parameters of type t, which are called x and y, and returns a value of type t. And essentially it just checks if x is less than y, and if x is less than y, it returns x, otherwise it returns y. So this is just computing the minimum of x and y and returning it. The next template function we have here, it's called sqr. It takes a single parameter. The template itself takes a single parameter. The parameter called t is a type because of the type name keyword here. Again, we could also say class. It would make no difference. And the function sqr, it has a single parameter to the function, which is type t, and the return type is t, and the value that's returned is just x times x. It's taking the parameter that's passed in and basically squaring it. The next template that we have here is called swap. It has a single template parameter called t, which is a type parameter because of the keyword class here. Again, we could also say type name, it makes no difference. The function takes two L value references to t as parameters, which are called x and y. And essentially what it does is it just swaps the value in x and y. It assigns x to a temporary variable, then assigns y to x, and assigns the temporary variable to y. This will have the effect of swapping the values of x and y. And then the function has no return value. And then the last template that we have here has two template parameters. The first template parameter is a non-type template parameter. We don't have type name or class appearing here, so this is a non-type parameter. And in particular, it's an int value, an integer value. It has a default value of 1, so if we don't explicitly specify this parameter, it will default to 1. And then if we look at the function is called increment by. It takes a single L value reference to t, called n, as a parameter. And if you look inside the function, all it's doing is it's taking n and adding to it the value capital N. So it's just going to increment this variable by whatever this constant capital N is. And because it defaults to 1, if we don't specify the value of n, it will just increment by 1 the value of n here, and then it returns a reference to that value. Earlier when we talked about functions, we talked about overload resolution, and the basic idea behind overload resolution is that in C++ you can have multiple functions with the same name, and then the decision about which particular function to get called when you use that particular name is based on the number and types of the parameters that are passed to in the function call operation. As soon as we have template functions, this adds a new dimension of complexity to the mix in terms of overload resolution, because now not only do we have the possibility of choosing between a number of non-template functions, but there might also be template functions that we could call as well when we're doing overload resolution. So the rules for overload resolution when we look at things in the context of template functions work in the following way. First, the compiler will look for a non-template function that can be called with 0 or more trivial conversions. And trivial conversions are things like converting between t and a const reference to t, for example. And if the compiler finds such a function that can be called, it will call it. If not, it proceeds on to look for a template function that can be invoked with 0 or more trivial conversions. And if it finds one, it calls it. If not, it proceeds on to option number 3, which is it looks for an ordinary non-template function that can be called with some conversions, some non-trivial conversions. Things like conversion operators or type promotions and so on. And if it finds such a function, it will call it. And in each of these 3 steps above, if more than one match is found, in other words, there's more than one equally good function that could be called, the call is deemed to be ambiguous and this is an error. In other words, the compiler, if it has a number of equally good choices of functions to call, it will never just randomly call one. Instead, it will say, hey, there's more than one equally good function to call. I don't know which one I should call. Please fix your code and make it more specific so that I know which function you really intend to have called. One important thing to note in the above steps is that a template function is only used in the case of an exact match up to trivial conversions. Unless you go out of your way and there is a syntax whereby you can explicitly force a template function to be called. But if you don't, unless you explicitly force a template function to be called, it will only normally happen in the case that there's an exact match up to trivial conversions. So below I have a code example to help illustrate overload resolution in the context of template functions. So you have a template function called max. It's templated on the parameter t, which is a type. And again, this particular function max, it just computes the maximum of its two parameters, x and y. So it checks if x is greater than y. If x is bigger, it returns x. Otherwise, it returns y. And the return type has type t, and both of the parameters have type t as well. Then we have this function down below called func, which has 4 parameters. 2 parameters are integer, int, I and j, and 2 parameters of type double, x and y. And then we have a bunch of function calls to max that are made below. And what we want to look at is what's going to happen for each of these function calls. What function is going to get invoked due to the rules for overload resolution. So in the case of this first function called to max here, both of the parameters have type double because x and y above here are defined to be double. So x and y have type double. So we get an exact match for this template here if we choose t to be double. Because if t is chosen as double, the first parameter is double, the second parameter is double. So these match the parameters here, which are both double. So this function call will result in max double being called. In other words, the version of max where t is chosen to be double. In the case of the next function call here, we're passing 2 int parameters. I and j both have type int. So this particular function call here would be an exact match for this template if we choose t to be int. If t is chosen as int, both of these parameters then have type int, which matches exactly these 2 parameters here. So this will result in the function call to the function max int. In other words, max with the template parameter t chosen as int. If we go on to this next function call here, max ix, this will actually result in an error. The reason why is that there's no choice of t that we can make here which will be an exact match up to trivial conversions for this function call, because the first parameter I has type int, the second parameter has type double, and no matter how we choose t here, we're going to have that at least one of these 2 parameters, one of the 2 arguments that are passed to the function are not going to exactly match these 2 types here. At least one of them is going to require a non-trivial conversion. And again, templates won't normally be called if non-trivial conversions are involved unless you explicitly force it to happen. So this will result in a compile error, this line of code here. If you go on to the last line of code here, we can fix the problem on the previous line by explicitly saying I want a particular version of max to be invoked, the max template function. So I can say max double, which is saying I explicitly am referring to the version of the max template where t, the template parameter, is chosen to be double. And in this case, this will compile fine because we've resolved the we've basically forced the template function to be called, whereas on the previous line here it wouldn't have been called because there is no exact match up to just trivial conversions. Now there's another important issue with respect to templates that I need to discuss, but before I can do this I need to introduce the notion of a qualified name and a dependent name. So first of all, I'll start out with qualified names. A qualified name is simply a name, in other words an identifier that specifies a scope. So in this code example that's shown here, an example of a qualified name would be the name cout. It's qualified because we're explicitly identifying the scope in which this identifier lives. The cout identifier lives in the scope stud, the namespace stud. And another example of a qualified name is endel here. This is a qualified name because we're specifying the scope in which this particular identifier lives. It lives in the stud namespace. So basically, if you have a scope resolution operator, the colon, you have a qualified name because you're specifying the scope in which that identifier lives. I would be an example of a name which is not qualified. In the code for a template, sometimes the situation can arise where a name depends on a template parameter, and such a name is said to be dependent, or it's called a dependent name. And I have a code example on this slide to help illustrate the notion of a dependent name. So we have this template function called func, It's templated on a single parameter, capital T, which is a type because of the class keyword. And then the function itself has a single parameter called x, which is a const L value reference to T. And then inside this function, we have this expression T::: magic value. So obviously magic value is some member of the class T. And notice that T is a template parameter. So this particular name here, magic value, depends on the meaning of T. So this T::: magic value is a dependent name. And as it turns out, sometimes we care a great deal about whether a name is dependent, as we'll see. As it turns out, due to the syntax of the C++ programming language, sometimes ambiguities can arise in the code for templates in terms of what the meaning of a name is. Does a name a type, or does it name a non-type, and so on? And in order to resolve this problem, what the language does is it says that anytime you have a qualified dependent name that appears in the code for a template, the compiler will automatically assume that that name does not name a type unless you explicitly put the keyword type name before the name to say, hey, this actually is a type. So for example, in the code example that I have below here, we have a template function called func. It has a single template parameter T, which is a type because of the word class here. And then inside this function, we have two qualified dependent names. Stud: vector T: const iterator. This is a qualified dependent name. It's qualified because of the use of the scope resolution operator in the name. It's a dependent name because of the fact that const iterator, the meaning of const iterator, depends on what T is. T is a template parameter, and the meaning of const iterator depends on what we choose T to be. Because for different choices of T, in principle, it's possible that this could be a type. Const iterator could be a type. It could be a non-static member, data member. We don't really know. So because the compiler can't really tell by looking at this template what the meaning of const iterator is, we have to tell it that this is a type by putting the type name keyword before it. If we leave this out, the compiler will assume that const iterator is not the name of a type. And then this would result in a compile error because this line of code will make no sense if const iterator is not a type. And then on this line down below here, we have another example of a qualified dependent name, the stud: vector T: value underscore type. This is another qualified dependent name. It's a qualified name because of the use of the scope resolution operator in the name. It's a dependent name because the meaning of value underscore type depends on this template parameter T, because if you look up above here, T is a template parameter. So this value underscore type depends on T, so it's a dependent name. So because it's a qualified dependent name, in order to indicate to the compiler that this should actually be treated as the name of a type, we have to prefix it by type name. Again, if we don't put type name here, the compiler will say, hey, this is a qualified dependent name. I'm going to assume it's not the name of a type. And then this will result in a compile error because this particular line here doesn't really make any sense if this is not the name of a type. On this slide, I have a code example to illustrate how ambiguities can arise when qualified dependent names appear in template code. So let's look at the example. On the first line, we have a global variable called x of type int that's initialized to 42. Then the most interesting part of the example is our template function called func. This template function is templated on a single parameter t, which is a type because of the keyword class here. And what's important about this particular function is that somewhere in this function we have a line of code that looks like line 11, where we say t::, foo, and then some other stuff. And basically what's at issue here is because of the syntax of the C++ language, there's two completely different things that this line of code could mean. And what's at issue really is what is the meaning of t::, foo? Is foo the name of a type, or is foo a non-type? If foo is the name of a type, then this line of code, line 11, would correspond to a variable declaration, a declaration of a local variable x whose type is pointer to foo. But this is not the only possibility. t::, foo could also be a static data member of the class t, in which case this line of code would mean take the static data member foo and multiply it by x, where x is this global variable here, and then throw the result away. Now both of these are equally valid lines of code, and equally valid kind of interpretations of this line of code, but obviously the compiler has to know what you really meant. It can't make sense of your code if it's not really sure quite what it means. And both of these possibilities can arise because, for example, this template could be invoked using a line of code which looks something like this, where we're passing in as a type parameter the type contains value, which is this type up above. And in this case, foo is a static data member of type int. However, we could also invoke this function func, passing a type as a parameter like contains type, which is the type shown above here. In this case, foo is a type member of the class. In other words, foo is a nickname for the type int. So both of these situations can arise in practice where t::foo, it could be a type, t::foo could also be the name of a static data member, but the compiler can't tell just by looking at the template by itself. So this is why in the language the rule that's adopted is if you have a qualified dependent name and you don't specify explicitly that it's a type, the compiler will assume that it's not a type. So for the code as we've written it here, the assumption by the compiler is this does not name a type. Therefore, the second function call here would fail to compile, but the first one would be successful.